Hello everyone. I'm going to give you an introduction to capacitors. Okay, so capacitors are passive components like resistors, and this means that they cannot generate energy. Okay, so what capacitors do is they store energy in an electric field. You have two parallel plates and they store charge. They absorb energy from a circuit and can release energy back into a circuit. So the symbol for a capacitor are the parallel lines. Okay, so then they that represents the actual physical structure of the capacitor. Two parallel plates where current can't flow through the plates, and there's some dielectric that separates the charge from the two sides. There's a picture of some capacitors here. Capacitors come in a non-polarized form, so that means positive or negative voltages can be applied to either side. And then the other kind of capacitors are polarized, and they have a different symbol which denotes the positive side from the negative side. So there's an anode and cathode. And these capacitors have symbols on them which let us know which side is the negative side. So these are dashed lines on the side of the capacitor, and they represent the negative side, and the negative side is the short leg of the capacitor, just like how it was with the diode, with the LED rather, that we saw. So the negative side corresponds to this side, or the short side, right, is the negative side. The long side is the positive side. So and if you put a capacitor backwards, a polarized capacitor backwards, most likely you're going to damage it. Okay, so as I said earlier, capacitors store energy as a separation of charge or accumulation of charge on the two parallel plates of the capacitor. And when you have a charge accumulated on a capacitor, there's energy, and it's stored in the form of an electric field. Okay, so that's the energy that's stored on a capacitor. So then we can say that the capacitor holds a certain amount of charge, and this is the equation that's related. So the charge on a capacitor is equal to its capacitance times the voltage of the capacitor. So the units are Q, or the symbol is Q, which represents the charge in coulombs. C is the capacitance in farads. That's the unit for capacitance, farads, and V is voltage. So the relationship between the units is that if you have a capacitor of capacitance 1 farad, which is a lot, and if you have 1 coulomb of charge on it, that capacitor is going to have 1 volt across it. Okay, and then we can do something very clever. If we take the derivative, the time derivative of that equation, we get dq over dt being equal to c dv dt. Okay, and if we note that current is equal to the charge per unit time, charge flowing per unit time, or dq dt, and then we can rewrite that derivative as I is equal to c dv dt. So that is an extremely important equation, and you should know it very well. Okay, and so of course I is in amps and time is in seconds. Okay, so now to understand this a little bit better, what would be the current if there was a constant current, a constant voltage applied to a capacitor? Okay, so what would that look like in terms of a circuit? Well, let's say we have a 5-volt voltage source being applied directly to a 10 farad capacitor. So that is an example of that situation. What would be the current that is flowing through here? What is the current? Okay. So, if the voltage is constant, then that means that the change in voltage per unit time is going to be constant because of the voltage is constant. So, and remember that voltage that's across the 10 farad capacitor is like this. We have 5 volts across here, just like the symbol says, and it's in parallel. 5 volts is right across the capacitor. Okay, so if our dV dt is equal to 0, and its units is volts over seconds, then if we apply our equation, I is equal to C dV dt, then plugging in the values, we have the 10 farad capacitor, and then we multiply it by dV dt, which is 0, we get 0 amps. So no current flows through the capacitor when you have a DC voltage on it. So we say that if you have a DC current, we say a DC current doesn't flow through a capacitor. It's when there's a DC voltage applied, so an unchanging voltage applied, then 0 current will flow through a capacitor. And you can actually kind of see that there's an analogy with the oscilloscope that we use in the lab. When we put it on DC coupling, it removes, or rather, if we put it on AC coupling, beg your pardon, when we put on AC coupling, it removes the DC component. So it's as if we put a capacitor in series with the voltage probe, and that blocks any kind of DC or constant voltage. Okay? So now let's develop another relationship for the capacitor. So we know the current of through a capacitor with respect to the voltage. So now let's find the voltage in terms of the current for a capacitor. Okay, so we know I is equal to C dV dt, and then if we just multiply both sides by dt and then take the integral of both sides, we have this relationship. And don't be distracted by the change of variables on this side. That's just to help us get the right values for when we do the integration. Okay, so then if we take the integral on the right hand side, we get C times V of t minus V of t naught. Okay. Now, of course, what is that T naught? So let's double back on here. So this is at the initial time, right? So this is the voltage at the initial time going to some time in the future to some voltage in the future, okay? And that's a voltage expression, okay? So then, if we just rearrange those terms to solve for V of t, we get the expression that you see at the bottom. V of t is equal to 1 over c times the integral of the current during the time interval of interest, and then plus the initial voltage. Okay, so that is a very important equation, and you should know that one as well. But you can develop it from I is equal to C dV dt. Okay, so now we often make t0 being equal to 0, so times 0. So what we can see is this t0 going to 0, t0 going to 0, and now that'll result in a little bit simpler expression. So let's make sure we understand what this equation is saying. So this V of t0 or t naught, initial voltage, that's the initial voltage on the capacitor, okay? The integral of the current times the reciprocal of the capacitance, that represents the voltage buildup on the capacitor. So if we have a capacitor and the voltage will build up and build up depending on the current that's flowing. Of course, it can build up in a negative direction if the current is leaving the capacitor, right? Or if it's removing charge from the capacitor. Okay, and then of course VFT, that's the total voltage across the capacitor. So you should know this equation. Okay, so now let's consider a scenario. What will be the voltage across a capacitor if there was a constant current applied to the capacitor? Okay, so what does that look like as a circuit? So we have a current source that has a constant current, okay, so a value I, and it's flowing into a capacitor of value C, and the voltage across that capacitor is VFT. So then the equation that describes this phenomenon is shown here, okay, and then so this is the equation that we saw earlier, and then if we resolve it, now we notice that of course I is a constant, right? So we can remove it outside of that integral, so that's why it appears out here, okay? And then when we take that integral, and resolve it, we get t, okay? So then you can see that this equation is looking like a familiar form of a y is equal to mx plus b, okay? So this right here, this is the slope, right? T is the variable, okay? And what's v0? What's v0? That's the y-intercept, right? Okay, so what would that look like in a plot? Well, this is our y-intercept right here, okay? V0, that's the initial voltage. And then we see the plot, that's just a constant slope, right? Because I is a constant, C, the capacitance, is a constant, so you can have a constant slope. And that slope is dV dt, of course, with value I divided by C. And we see the familiar form from that slope, I is equal to C dV dt, okay? So now, let us look into the power and energy relationships in capacitors. Okay, so now, if we use the passive reference convention, then we have current flowing into the capacitor, okay? That's this I, and the voltage across it is in this form, okay? Positive to negative. Okay, so then, what's the relationship? P is equal to VI, just like it is in a resistor, okay? So, and this is universal for electrical components, okay? Power is equal to the voltage across them times the current flowing through them, okay? So then, we can, and of course, you know, P is equal to VI is the same, we could have written it as a function of time, so this is the equivalent thing, right? We can say P of t is equal to V of t times I of t, right? So that's the more general way of writing that relationship. Okay, so now if we plug in what we know about I being equal to C dV dt, we can get this relationship. V times C times dV dt is equal to the power. And we can take the other form and plug in what we know about V of t times I. So then we have this relationship here. So these are all important relationships that you should be familiar with, okay, for power. So then let's look at the energy in a capacitor, and this is very interesting. So recall from the beginning of the course we said that power is the time derivative of energy, okay, the change in energy per unit time. Okay, So we also know that power is equal to VI, and we could plug in what we found earlier here, and then we can manipulate by taking this part and taking this part down here and operating. So then if we cancel the DTs, right, we get this relationship, and then integrate both sides and use a kind of like a dummy variable to make our math work out a little bit better. And then when we resolve those integrals, we get the relationship that energy is equal to 1/2 CV squared. Okay, so that is a very important relationship, so you should know that very well. Okay, energy stored in a capacitor is 1/2 of the capacitance of that capacitor multiplied by the square of the voltage across that capacitor. Okay, so that's the energy stored in a capacitor, and that energy is stored in the electric field as we discussed earlier. So now this equation here, like really, it's really interesting, right? And it should remind you of the things that you know about from before. Remember, kinetic energy is equal to 1/2 mv squared, right? Or rotational energy is equal to 1/2 the moment of inertia times the angular frequency, or the frequency of rotation. Okay, so those are all related, aren't they? Okay, so then now let's look at how capacitors in series and capacitors in parallel behave in terms of their equivalent capacitance, similar to how we found equivalent resistances back when we were doing series and parallel. So now let's consider parallel capacitors. Okay, so imagine a circuit like this where we have 3 capacitors in parallel, capacitor C1, C2, and C3, and let's say that represents the capacitance values. So C1 might be 10 microfarads, C2 might be 1 microfarad, and C3 might be 1 picofarad. Okay, and imagine that we have a voltage across them. So let's start analyzing this to see how to develop the relationship for the equivalent capacitance for parallel capacitors. So let's represent that there's a current flowing. Okay, so there's a current flowing into the parallel capacitors, and in each branch through each capacitor there's going to be an I1, an I2, and an I3. Okay, so then let us do circuit analysis on this, and let's do KCL. And KCL works for capacitors too, not just resistors. So if we define a node A up here, so our node A is up here, right? That's node A. We define the reference node. Okay, so we'll do KCL at node A, and we're going to get the current flowing in is going to be equal to the current flowing out. So I is equal to I1 plus I2 plus I3. So now, for those I's, let's sub in our relationship I is equal to C dV dt. So then the relationship is like so. For this I1, it's this. For this I2, it's this. This I3, it's this. Okay? So then what did we do here? We have C1 associated with I1, and we have a dt, okay, dV dt, okay, and we have the same dV dt across all of them. So how does that work? Well, it's because we have the same voltage across all the capacitors. Because they're in parallel, the voltage here, plus or minus V, like this, across the first capacitor, which is due to the voltage source, is going to be the same as the voltage across C3 and C2. Okay, so that's why we can say that dV dt is the same for all those capacitors. Okay, So then we can go ahead and factor out that dV dt, and so we have C1 plus C2 plus C3, okay? And we can say that that is our equivalent capacitance. We'll just define the sum of those capacitors as our equivalent capacitance. So then we could write a general formula for the equivalent capacitance for capacitors in parallel, like so. C equivalent is the sum of all of the capacitors in parallel. Okay, so that is a relationship that you should know. Memorize it. I think it's a little bit intuitive. And let's make the statement that capacitors in parallel add like series resistors, okay? Because if you had a bunch of resistors in series, you would add up their resistances to get an equivalent resistance. For capacitors, it works that way, but for parallel capacitors. And one thing that we can do is think about, like, intuitively, how does that work? So imagine that we had a large capacitor, okay? It has some capacitance, and we just broke it up into 4 parts, and if we added up all those 4 parts, they would add up to that large capacitance. So we can see that they're adding up, okay? The logic of it seems to make sense. So this is how I remember the formula, okay? Or the relationship, let's say. So then we've done parallel capacitors. Let's do series capacitors. So to analyze or develop the relationship for capacitors in series, what's the equivalent capacitance? Let's consider a current source, a constant current source, driving current into 3 series capacitors of values C1, C2, and C3. Okay? So now, to analyze this, let's recognize that there's going to be some voltage across the current source of value V, and each capacitor is going to have its own voltage across it, a V1, a V2, and a V3. Okay? And then let's do circuit analysis on this capacitor circuit, and we could use KVL. Okay? So KVL works for capacitor circuits as well. So if the circuit is in a loop, so we could do KVL around the loop, and we see that the voltage on the source is going to be equal to the sum of the voltages of the capacitors. Okay? Now, if we assume that the initial voltages are 0, so they're starting off with 0 voltage, then it makes using our that integral equation easier to use. Okay? And then we're just going to sub in that equation. So then for V1 we're going to have this, right? For V2 we're going to have this, and for V3 we're going to have this. Okay. So now what you'll see is that each of those terms have this integral in common, right? And how is that? That represents the current flowing through them, okay? So then the current flowing through this circuit, right? Of course it's I, right? So that's why we can have the same current defined. So then if we factor out that integral, that current, the integral of the current, then we can pull out all of the constants, which are the capacitance values. So it's V is equal to 1 over C1 plus 1 over C2 plus 1 over C3 times the current. Okay? And then if we just call the sum of those reciprocals of the capacitances to be 1 over C equivalent, then we can develop our relationship for capacitors in series. Okay? And this is the relationship there. And you should memorize that and recognize that that is the same relationship that resistors have in parallel. Okay? So then, just like for resistors, like of a constant value, whether they're in series or parallel, there's a handy shortcut for knowing what the values are. There are there are similar relationships for capacitors. So imagine we have n equal valued capacitors. Let's say n is 10. Let's say we have 10 equal valued capacitors. And equal valued means that the capacitors have the same value. Let's say 10 microfarads, okay? So then what would be the relationships? So starting in parallel, the equivalent capacitance is just n times the capacitance value, okay? So in terms of a circuit, it looks like that. Let's say we have n capacitors of value C, okay? They're all, the equivalent capacitance is going to be n times that capacitance. And then for the series case, we're going to have the C equivalent being equal to the capacitance value divided by the number of capacitors, okay? So divided by that n. So then that looks like this. So we have series capacitors of value n, we have n of them. So if it's 10, if n is equal to 10, then we have 10 capacitors in series. And that equation holds for this. Okay, so now, knowing what we have, here we know about the energy stored in a capacitor. We know about what the capacitance is in parallel or in series. So imagine if you were going to make an energy storage system using capacitors, so it's going to be like a battery, right? And should you connect those capacitors in series or in parallel to maximize the energy that is stored in that system that's just made out of the capacitors, okay? So how is that going to look like? So let's explore this and see what we can come up with. Okay, so now we know that the energy stored in a capacitor is 1/2 CV squared, okay? C is the capacitance, the total capacitance or the equivalent capacitance, and V is the voltage across that capacitor, okay? So now imagine if we had a capacitor of value C, some value, right? And there's such a thing called supercapacitors, and their capacitances are up in the range of farads, okay, which is huge for a capacitor. So now, but what about the voltage? So now, for a capacitor, every capacitor has a maximum voltage that you could put across it, okay? If you exceed that voltage, then the voltage is going to be too much, and it'll punch through the capacitor and destroy it. It'd be like breaking down the dielectric, okay? So there's a maximum voltage that you can apply to a capacitor, and I've denoted that as Vmax, okay? Okay, so then if you want to maximize the energy storage, you're going to want to put the maximum voltage you can apply on it, okay? This is a theoretical thing, okay? This is not like a 100% practical analysis. There's many other factors to making such an energy storage system. This is more like playing with the equations that we've developed and the relationships so we can understand them better, okay? So, but in this example, the maximum voltage you can put on a capacitor is Vmax, okay? So then let's analyze this. Okay, so in parallel, all the capacitors are in parallel, okay? So what's the value going to be? What's going to be the energy? Well, we're going to have to denote that maximum voltage across all those capacitors is going to be Vmax. And then the equation is going to be 1/2 that we know, right? 1/2. And then the equivalent capacitance is for parallel capacitors is N times C, okay? So the effective capacitance is much greater, okay? They're in parallel. And then the maximum voltage that we're applying is Vmax, and we square that to get the energy, okay? So that is the equation for this case. This is the total energy of these parallel capacitors, okay? So then let's analyze the series case. So this is a little bit more tricky, okay? So what's tricky about it is what is the voltage across this setup, okay? How does Vmax work? Okay, well, we're going to have a Vmax for every capacitor, okay? Each capacitor is going to have its own Vmax. And then when we put them in series, those Vmaxes are going to add up, aren't they? Right? For a total Vmax for that series combination of those capacitors. So then the effective Vmax for that series set of capacitors is going to be N times Vmax, which it should make sense because they're all stacking up one on top of each other. So then what happens to the energy? Okay, well, we have that equation, right? So we have energy is 1/2, and then times the equivalent capacitance of series capacitors, C divided by N for N equivalent capacitors, and then the voltage across the entire setup is N times Vmax, and we square that, okay? So then, if we work it through, the N cancels, right? One of the N's cancels, right? One of the N's cancels in here. So that's just 1, and that's a 2, right? Okay, so then what we notice is that both of those equations are exactly the same, okay? So that means that they have the same energy, okay? So that's a really unusual result, okay? So in this ideal scenario, it doesn't matter whether you connect the capacitors in series or in parallel, they'll hold the same amount of energy, okay? For a practical system, there are, of course, other considerations, right? But this is working through the concepts of parallel capacitors, series capacitors, and the energy stored in them. Okay. The next presentation is going to be how to analyze a capacitor circuit in terms of its energy, its power, and voltage and current relationships. Okay.